Hello, I'm Mr. McBrien. This is TEJ3M, Arduino 5, Inputs. Yesterday we talked about pulse width modulation and its application to controlling devices that aren't easily given power outputs. Today we're going to talk about sensors and push buttons primarily. So instead of outputs, we're going to be talking about inputs today. And of course, the Ontario curriculum wants us to do this, developing a program that interacts with an external device. And that's what we're going to talk about, various ways of doing that today. So, why are inputs important? Well, the thing is, the situation around our device will not remain the same at all times. And in fact, devices need to be able to react to their environment. That's a good chunk of why we write programs in the first place. Now, I've given you a little challenge. Can you think of examples of devices that don't interact with their environment? Stop the movie now and see if you can list a few. See if you can think of a few that do not accept any input from the outside world. I think you'll find it fairly challenging. Okay, maybe you've listed a few devices, thought of a few. I'm not going to list any here. Hopefully you could think of a couple. But here's the second part of the challenge. Can you think of devices that react to their environment? And in fact, this is an almost trivial exercise because almost any electronic device reacts to its environment in some way, whether it's an input system, a sensor, or what have you. Okay, so we want to be able to take our processing algorithms and we want to have them make choices based on the outside world. And we've already discussed constructing loops that can monitor for input, particularly so far from the serial monitor. But we can also monitor given pins, looking for electrical signals. And our sketch, of course, then can change its behavior based on the value from a given pin. This change in behavior can be as simple as going to or from a standby mode, or it can be almost as complicated as we can conceive. Now this is really the 2 hours traffic of our stage today, even though we're going to backtrack a little and talk about our options for inputs. So I want you to put a pin in this idea of pins while we talk further about inputs. So an interactive system, those loops that we talked about, we can simply do things like monitor a switch, checking to see if it's pressed. If it's not, we return to our monitoring stage. And we can sit and reiterate that monitor process over and over again until our situation changes. So when, in this case, our switch is pressed, we can then start a given function, do something that responds to that press of the switch. Now, there are other, options besides switches for us to think about in terms of inputs. So switches are examples of user inputs. There are other kinds of user input as well. We can accept inputs from the internet, from a network. We can accept inputs from sensors, and there's lots of other devices as well from which we can get inputs. So there are a lot of different options, each of them determined by the application area of our given device. In terms of user inputs, when we connect hardware, the user can influence the device. Switches are obvious. Dials like potentiometers can be used. Keypads are a little bit complicated to implement, but can be done. There are even touch screens that we can implement with Arduino. And there's lots of other ways for a user to interact with the device. So some example applications, we can have a toggle where a user presses a switch, the device functions until that switch gets pressed again. extremely simple user input. Or we can have a keypad and a user can type in a passcode to disable a security system, these kinds of things. Now, switches are largely yes-no, and they largely react to fingers. Sensors react to many, many other things. So there are lots of kinds of sensors available to our Arduino. The key thing around a sensor is that its electrical behavior has to change in response to that thing that it's monitoring. And ideally, its electrical behavior will not change with any other change in stimulus. So it's focused on that one idea, that one item. So, some examples of sensors. We can have sensors that will detect light or lack of light, infrared radiation, moisture, heat, much more we can have detected with our sensors. Example applications. A night light can turn on an LED if there's no light hitting its sensor, just using a simple, inexpensive light-dependent resistor, and we've already played with one of those. We can have an IR sensor that looks for a pattern of pulses, and based on that, changes the power to a device. Now there are other kinds of input. We can accept input from the internet. This is because Arduino shields are available that support Wi-Fi or Ethernet. So once we do this, an Arduino can be controlled by an app, or it can monitor websites like Twitter, and we've seen the example before of that. We also may not directly use the internet. We can use a network location to have the Arduino communicate with a different computer that might be running a very complicated program, and using a network location to communicate to the Arduino and having the Arduino react to the results from a program from a different computer. So some examples of internet applications. We can have an iPhone app sending commands to an Arduino, maybe controlling a thermostat. We could have the Arduino monitoring a website and sounding a siren and a flashing red light when the Toronto Maple Leafs score, if they ever play a game. There are other devices that aren't precisely sensors. So we can connect any kind of electrical device to an Arduino as long as it has predictable electrical output. And so we can do things like connect Bluetooth and optical IR remotes, things like this. Whether or not we have to purchase a shield depends on the precise situation. So some other examples of fun applications. Here's a cool one. A romantic geek connects a lockbox to an Arduino with a GPS shield. And he hands the lockbox to a woman with a series of clues. When she gets to the location in the clues, the lockbox opens and reveals the engagement ring. So certainly a fun application. Okay. Now, so we've seen that there are many, many different inputs that we can accept with the Arduino. We're going to scale things back a little and look at the simplest of these inputs for now. And in order to do this, we need to talk about how the Arduino detects and uses inputs. Of course, it depends on the type. Usually we're going to incorporate a status check in a loop, and each of these will be coded in a different way. We're going to focus on two key commands today. So we're going to look at reading a given pin. If it's an analog value that we're looking for, we use the analog read command specifying the pin number. If it's a digital, then we use the digital read command and the pin number. And when we do this, when we trigger this command, we get the potential at the pin number gets assigned to our variable. Either yes, no in the digital case, or a given numeric value in the analog read case. And this is our absolute core skill. We need to be able to read these pins to be able to implement even the simplest of devices. Back to this digital analog thing again. Well, yes, we need to be able to differentiate between a numeric result and a yes-no. So as a reminder, digital is on and off. Analog, on the other hand, gives us a value. So classic example of an on-off would be a switch. It's either pressed or it's not. Whereas most sensors tend to give a value. However, there are some sensors like the line follower on the right that are digital. Essentially, they evaluate the inputs and they have an onboard processor that decides if it is a yes or a no. And what they send back is, again, that digital output from its perspective, input from the Arduino perspective. So if you're using these pins, of course, the voltage, the potential that's available to us is 0 to 5 volts. If we're looking at analog results, the value will be from 0 to 1023. How many bits is that again? I'll let you work that out. Now, there is a little bit of circuitry that we have to discuss before we go any further. We can make a detector, of course, based on the value that we get. We can make a detection system, but the value itself depends on the device and depends on how it's configured. So let's use an example to illustrate this, and it's an example that's already fairly familiar to us. Our simple nightlight implementation. So what we want is the resistance of the LDR. We already know that the resistance changes with light hitting it. The resistance drops considerably as soon as light hits the LDR. So the Arduino has to be able to interpret the change. And so we design a careful circuit to allow us to do that. So how do we do it? We're not going to measure resistance directly. Arduinos don't work that way. We measure the resistance of that LDR indirectly. So what we do is we run 5 volts across that LDR plus another resistor. So we run power across that combination. And we're going to measure the voltage drop. So we're going to pull the voltage from between the two of them. And you can see the circuit in the bottom right. And so that voltage drop is going to give us our result. We'll measure, in this case, the voltage at A naught. Now let's have a little closer look. So the circuit looks like this. We measure the potential difference between A naught and the ground. And that potential difference will vary considerably depending on the resistance of the photocell. If you don't remember voltage drop, we can analyze this. Remember, I always encourage you to consider the extremes of the potential values, what you might get, pardon the pun, and those should help you to understand what should happen here. Now notice if the photocell, if the LDR had 0 resistance here, that would put the potential at A naught the same as our 5 volts. We would measure 5 volts if that resistance were 0. Because it'd be just like a wire was there. If the resistance is very high, then we start to look at that voltage drop equation. But if you don't remember it, we can do it as a simple thought exercise. And we can say, okay, if the resistance here is very high, essentially there's going to be most of the current is going to get pulled away by this fixed resistor here. We are going to, most of the energy from the electrons is going to be sapped by going through this high resistor here. So once we reach this point, it's at a very low energy point and our voltage will be very low. So high resistance here, we measure a low potential at A naught. Low resistance here, we see something close to 5 volts. Okay, so once we have that once we have that potential measured at A naught, we can calculate the light level and decide when to turn on our LED to implement our night light. Now here's where the serial monitor starts to show its value. We could sit and theoretically calculate what voltage we could expect and all these kinds of things based on equations for voltage drop. But in fact, the theory may betray us because we're not really sure how that LDR is going to behave. We don't know what light levels we're going to have. What we can do is we can do this thing experimentally very quickly. So we can implement a temporary device that reads the potentials like we just said and just prints them to the serial monitor. So we can get our analog reading when we've got our light shining on our LDR and when our hand is over top of the LDR. And with those two values in hand, we can design then our logic. Use that value in any further calculations. So I'd like you to try that. Use those ideas to create your first implementation. So breadboard some LEDs with Arduino output pins. You've already got most of the code for all that stuff. But now I'd like you to implement a button. Notice the button will take the place of the LDR. Monitor button to see if it gets pushed. And if it gets pushed, just turn on the first LED. And your sketch should, if you press the button a second time, turn off the LED. So there's a lot to unpack there, actually. It's a good, interesting beginner sketch. Now, there is one key trick here. You've got to remember to put a delay in between your monitoring steps. Do you remember how to put a delay in place? Look it up if you don't recall how to do it. If you don't have your delay in there when you're checking the status on something like a switch, you check it too fast. So when a human being presses the switch, if you check it too often, it'll look like it's been pressed twice or perhaps 20 times because human beings do things rather slowly. So if you introduce this delay between checking operations, you're going to compensate for the slow execution that is typical in the physical world. And this is a good thing for you to keep in mind. For many of your implementations, you need to remember that things happen on a time scale where your program needs to realize that it may need to slow down and give the real world time to execute things. Now, there's an additional tool that may be helpful to you looking forward, and that's this idea that'll be quite familiar to you if you're a veteran programmer of if-else and else-if. So the syntax is here. Don't forget to check the references for the exact thing. But if statements check to see if something is true, and then they can execute a set of commands based on that statement. If the statement's not true, else can allow us to execute something else, to do something else based on it. And you can go ahead and read the documentation. These can get quite complicated as you go through. But they're extremely powerful for these ideas of checking a state and then deciding where to go from there. So in this case, we've got an implementation that all it does is if the button gets pressed, we turn the LED on. If it's not pressed, we turn the LED off. And that may or may not fit the logic of your sketch, depending on how you decide to implement. Now, one thing about this, some of us have lots of hardware lying around, some don't. If you don't have a push button lying around, it's no big deal. A button, when you push it down, is a wire. So you can just take two wires. Whenever you want to, quote unquote, press the button, just touch those two wires together, and you've got the same thing as a button. Buttons are good for final implementations and completely unnecessary when we're doing code development. Okay, but these if-else statements, you've really got to learn how to use these because they're going to come in extremely handy in the weeks that follow. Okay, so really, these are most of the skills that we needed for today. So once you've got your simple toggle up and running, you can go ahead and enhance that. You can use a button to increment between a series of LEDs. So keep an eye on your switch. Each time the switch is pressed, move from one LED to the next and scroll through them all. Now, the standard warning applies. Don't forget to make sure that every LED in your circuit is protected by a resistor or you will burn them out. Okay, so if you found those extremely easy and have them all done and want to work on something a bit more interesting, we can look at applying an analog value in a calculation. So a classic thing to do is implement an electronic thermometer. And the good news here is it's an inexpensive component if you're working with hardware. It's also available on Tinkercad if you want to implement in a simulation. So if we want the Arduino to function as a thermometer, we can implement the idea of pushing the temperature out to the serial monitor. We can get some of the math from the TMP35 datasheet. You can also look up example sketches online for this. Now, after you've implemented the ability to push the temperature out to the serial monitor, you can also implement a combination of the ideas that we've had from today. So you can take your LED lighting circuit and quickly turn that into a quick read thermometer. So what we can do is take our Arduino, calculate, accept the input from the TMP35, calculate the temperature, and then report the basic situation to LEDs. So if it's greater than 27 degrees Celsius, you can make it red. If it's around 24, you can make it yellow. If it's less than 21 degrees Celsius, which I sure wish it was right now, if it were less than 21 degrees Celsius, you can make it green. All right, so lots of fun things to unpack today. Our Arduino input pins monitor potential difference. They monitor voltage. The values we get out of them can be digital and on-off, or they can be analog, a range from 0 to 1023. We can use these inputs to look for things like button pushes or get values from things like sensors. So for your homework today, go ahead and work through those example circuits. start getting your sketches reacting to your environment. Don't forget to check for references online where you need them. There's also some hyperlinks here to the Arduino website for some of the key ideas we saw. Thanks very much. Have a great night.